Alright, in this video we will cover 9.3. So we begin 9.3, question 59 on page 39, and we're multiplying. These first 8 problems, I guess, are pretty straightforward. They're just multiplying. The idea is that they don't have to look alike or anything like that. You can just go ahead and multiply them together. So square root of 3 times square root of 7 is just square root of 21. Square root of 6 times square root of y is just square root of 6y. Square root of 7, square root of 2, let me give you a moment, square root of 14. Square root of 3 times square root of 14, square root of 42. Okay, so we'll go ahead and pause right there, but that's really just what these 8 problems are all about. Okay, and this is where we've got kind of the meat of this unit. This idea of simplifying a radical. Now, there's 2 main ways to simplify a radical. So I'm going to use 2 different colors here. I'm going to use blue for one method and red for another method. So the method I'm going to use in blue, I've got some numbers listed in blue up here. Those numbers are the perfect squares, right? 2 squared, let me get an arrow going here. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. You get the idea, all the way up to 10 squared is 100. So this is actually my preferred method, but that by no means it's the correct method or better of the methods. But this method says, okay, take that number and rewrite it. So take 20 and rewrite it as a combination of 2 numbers multiplying together. One of those numbers has to come from our list up here at the top, and we need the biggest one. So square root of 20, well, obviously the number we choose can't be bigger than 20 itself, so we're looking at 16, 9, or 4. Then the only combination we can come up with is 4 times 5. We know that the square root of 4 is 2, and so we take the square root of 4 to be 2. Notice it's not under a radical anymore. And we leave 5 underneath the radical sign, so 2 square root of 5. The other method is prime factorization, or sometimes called factor tree or a tree. It allows you to start with any multiplication you want. That's the advantage to this one. So how about 2 times 10? When you hit a prime number, you stop that branch. And a prime number is a number that can only be expressed as 1 times itself. So for instance, 2 is prime. 10, though, is not, because it's 2 times 5. But 2 and 5 both are. So we're done, and the end of our branches are 2, 2, and 5. So anytime we have a match, a pair, we can take that pair, and that pair goes to the outside. So 2 comes to the outside. When we don't have a pair, like 5 didn't have a buddy, it stays under the radical. So we get the same answer either way, but you've got to kind of decide what's your preferred method. Okay. 33. Now, this is an interesting one, and I probably shouldn't do this one second, but 33 is actually, well, let me show you the method in red first. 3 times 11. Well, both 3 and 11 are prime, and so neither of them have a buddy, right? So they're going to get a box because they don't have a buddy. They both then have to stay underneath the radical. So we multiply them back together, we end up with 33. This one is already simplified. If I tried the method in blue, I've got to pick a number from this list, so it's got to be smaller than 33, so we're looking at 4, 9, 16, or 25. None of those numbers, when multiplied times another number, can equal 33. 4 times nothing is 33, right? 9 and nothing is 33. So this is already simplified. Right, and again, we just kept the square root of 33 or so. This is already simplified. Okay. Let's do another example where it's not already simplified. So 98. So we're going to make this a multiplication of two numbers. One of them has to be from the perfect squares list. Well, 98 is like, way up here by 100. So we have a lot of numbers to choose from. We can make it a multiplication of any of these numbers up here. So we could do 81 times something. No, 64 times something. Ooh, 49. 49 times 2. Oh, that didn't work. There we go. So 49 times 2 is our multiplication that equals 98. Square root of 49 is 7. 7 square root of 2. Okay, let's say you use 7 times 14 as your multiplication. 14 is going to be 2 and 7. So we've got a pair of 7s. That comes to the outside. 2 doesn't have a buddy. Goes under the box. So whatever method whichever of the two methods you use. Now, with the method in red over here, this prime factorization, you could have started with 49 times 2. Then you would have broken 49 into 7 times 7, right? Like, we could have not started that same way. We could have went, well, I know that that's 49 times 2. Sorry about that. 49 times 2, and that's 7 and 7. So we have our pair of 7s and our 2 without a pair. So 7 root 2 is going to be how that gets simplified. Okay. I've left some of these other ones here for you to kind of practice, but I want to talk about 73. 73 is one where you may be tempted to try either of the two methods and just get started on it. But when the numbers are bigger like this, like we don't see 400 on our list, but my list stops at 100. It's important to note before we get started whether or not a number comes from this list. Because if it came from this list, we wouldn't do it. Like, you wouldn't, if the problem was square root of 36, you wouldn't try a method. You would just say, well, I know that's square root. Square root of 6. So if the number's on the list, we don't mess around with either method. So the point here is that 400 is on the list. It just, my list didn't get there. The square root of 400 is 20. So take your calculator and check the number to see if it's a perfect square. Like, you would check 750. It's not. 750 is not a perfect square, so you're going to have to do one of the two methods there. But you would start there. You would start to making sure it's not a perfect square. So there's your two different methods. You're going to see, I'll show you them again here in a little bit. All right. Our quotient rule. We actually kind of saw this earlier, but our quotient rule says I could break these apart if I wanted to. And the reason I would want to on this one is because both of these are perfect squares. And if either of them is a perfect square, if either the numerator or denominator is a perfect square, then break it apart and take their square roots. And you're done. Move that down a little bit. Okay, but on 77, neither 54 nor 6 is a perfect square, right? And those perfect squares are those numbers I had written in blue. So I don't want to break these apart. So I'm going to put them back together. Well, 54 divided by 6 is 9. Still under the radical, but the square root of 9 is 3. Now it's not under the radical. Okay. I don't want to break this apart because 60 is not a square root, nor is 5. So I'm going to keep them kind of together like this, and I'm going to divide them out, and that is 12. And 12 is not a perfect square, so I have to break it down, and I'm going to walk through both methods with you. So let's say I wanted that to be 2 times 6, and 6 is 2 times 3. So I got a pair of 2s, and I got a 3 all by itself. And so I simplified it. So that's our answer, not the square root of 12. We actually need to break it down. Let me show you my other method here. That's going to be square root of 4 times square root of 3. Square root of 4 is 2, square root of 3, right? So there's that same answer, whichever method I used. Here, one of these is a perfect square. So square root of 6 over square root of 49. That's a 7. And I can't break 6 down. There's no way to break 6 down. It's just 2 times 3. Like, there's no way I can simplify that at all. So this is our answer right here. A little bit messy, but that's okay. So if one of the numbers or both are a perfect square, then you separate them. If neither of them is a perfect square, then you divide it out and tackle whatever number you end up with. Okay. All right, let's take a look here. So now we're going to simplify, but we're going to simplify some variables. The idea behind simplifying variables is we have the square root of x to the 8th. For every 2 x's, I get to bring 1 to the outside. So 1, 2, 3, 4, 5, 6, 7, 8. That's what x to the 8th means. So I've got 2 here, I've got 2 here, 2 here, and I've got 2 here. So I have 4 pairs. And because we're dealing with a square root, we're looking for pairs. So I had 4 pairs of x's, so I have x to the 4th. No leftovers. 85. I'm going to look at this as 2 pieces. I'm going to first think about the square root of 100, which is 10. And then I'm going to look at c squared. So if I have 2 c's, how many pairs do I have? I have just 1. And so the square root of 100c squared is 10c. 28 r to the 4th. I'm going to look at this as 2 pieces. First, I'm going to think about the square root of 28. Now, I'm just going to show you my preferred method, but remember, you can use anything you want. You could tackle this as 2 times 14 and then break 14 down to 2 times 7. I'm just going to say I know this is 4 times 7, and I know the square root of 4 is 2, square root of 7. Notice I've left a little bit of space here because now I'm going to deal with the variables. I have r to the 4th. That means I have 4 r's. That means I have 2 pairs of r's. I don't like the way that turned out. I have 2 pairs of r's. So on the outside is 2r squared, meaning there's r squared means 2 pairs of r's, and then the square root of 7 is left over underneath. Square root of 40 over square root of w to the 8th. Well, w to the 8th is just how many pairs do I have if I have 8 w's to begin with? 4. Square root of 40, I got to do a little bit of work on that one because I need to break it down. I'm going to make that square root of 4 times square root of 10. Square root of 4 is 2 square root of 10. And there's our answer. Okay. Now we're going to ramp it up a little bit. We're going to talk about what happens when there's an odd amount of them. So a to the 5th. So I'm going to start by doing that same idea. 1, 2, 3, 4, 5. Looking for pairs. There's a pair, there's a pair. Ooh, that guy doesn't have a pair. So there are 2 pairs and 1 left over. Now, I'm not going to write 13 G's out, but I know that there are 6 pairs with 1 left over. Okay. So we've got 72x to the 3rd. First, I'm going to think about 72. I'm going to use my perfect square method, and that is going to be 36 times 2. Square root of 36 is 2. Leave some space. And again, I leave that space for the variables. I am dealing with x to the 3rd, which means I have 1 pair of x's and 1 left over. So this time I end up with 2x on the outside and 2x underneath the radical. And that is our simplified radical. Square root of 13q to the 7th. I need to start with the 13, but I can't break 13 down. It's a prime number. I can't. There's no simplifying it. So I'm looking at q to the 7th, and I know with q to the 7th, I can get 3 groups out of that. And 13q still left underneath. (75p to the 11th). I'm going to start with the 75, and I'm going to make that 75 is going to be 25 times 3. The square root of 25 is 5. I'm going to leave some space. I have 11 P's, which means I've got 5 pairs and 1 left over. Okay, where are we at here? So here I have u to the 5th and v to the 7th. So I'm just going to look at them separately. With u to the 5th, I can have 2 pairs with 1 left over. Sliding to my v's, v to the 7th, that means I have 3 pairs with 1 left over. $44, that's going to be 4 and 11. Square root of 4 is 2, leave some space. Square root of 11, so x to the 12th. I have 6 pairs. There are no leftovers. I've used all 12 of them. But y to the 5th, I get 2 pairs with the 1 left over. $103. So I've got a perfect square here, so I'm going to separate this. And let's focus on my numerator first. Y to the 7th. That's 3 groups with 1 left over. Square root of 81 is just 9. So I don't even need to break 81 down because it's a perfect square. D to the 6th, actually, that's 3 groups with, or 3 pairs with none left over. Okay. 106. So again, I'm going to look at this as 2 separate pieces. It's an H. All right. In the numerator, 17 is prime, so I still have that underneath the square root. 11 H's. H to the 11th. That's going to be 5 pairs and 1 left over. K to the 8th. That's going to be 4 perfect groups. All right. When we get down to 107 through 118, those are mixed reviews, so you've seen enough to be able to do those. I'm not going to go through any more of those. And then next video we'll talk about, we'll go into 9.4.